Hello, everyone. Good afternoon. Welcome to our joint talk on dynamical Lie algebras and Barren Plateaus by this huge Barren Plateau consortium. The reason why there's so many entities involved is that this is actually two papers, one by, loosely speaking, the JP Morgan team, and the other one, loosely speaking, the Los Alamos team, but there's many people involved. So I will be giving sort of comprehensive introduction to the math, and then Michael after me will be giving some more the interpretation of this work. Okay, let's get started. Good, so let's start with a brief outline of the context that I'm talking about. So I assume some of you may not be familiar with variational quantum algorithms, at least not the fine details. The things you should know is that variational quantum algorithms have an ansatz, which is a parameterized unitary. And often the useful ones are problem aware, which means that they change based on the problem. An even more refined subset of these is symmetric ansatzes, which is basically when the ansatz is only taken from subgroup, continuous subgroup of the unitary group. And we call this group the dynamical Lie group. Okay, so if you take a very non-symmetric ansatz, which is maybe the hardware efficient, that will generally express the entire unitary group, and in that case, the DLG is the entire unitary group. Then a brief reminder of Lie group theory is that the most useful thing to do when you're given a Lie group is to take the Lie algebra, which is the tangent space at the identity. And that often encodes in a very nice way some of the properties of the Lie group. In this case, the Lie algebra is termed the dynamical Lie algebra. Okay, now let me define seemingly unrelated concept, which is Barren Plateaus. So this is a very, very famous concept, I think first introduced by Jared here. Yeah, so this involves when you have such an ansatz with some parameters, and then you take the gradients of these parameters because maybe you're interested in some optimization. And this Barren Plateau phenomenon is where the gradients decay exponentially. This is a massive problem because you cannot train these ansatzes, at least not from uniform initialization. In practice, to calculate if you have a Barren Plateau, you need to compute something like this, which is called a second moment integral. And it's basically an operation that you apply on the measurement unitary, and it's like a twirling. But this is very complicated, and it's only really easy for classical Lie groups and some of their representations, and in general is basically impossible. However, to the rescue came this paper in 2021 by La Rocca et al., which suggested this conjecture, which empirically looks very true, which relates the decay of this gradient variance with the dimension of the DLA. So it's basically saying if the DLA decays polynomially, we don't really have a Barren Plateau. And this is very surprising because where is the DLA coming from? I mean, the previous problem was just, you know, just gradients and variances, and it's not really immediate. I mean, there's a hint here that you're taking an integral over the hard measure of the group, but in general, we don't know how to do these things, so what can we do? Well, we were able to prove this, but we needed to do one key realization first, which is basically all the examples that we had of this behavior were when the observable was itself part of the Lie algebra. And this gave the key intuition that we really needed to focus on the Lie algebra itself. So to understand the proof, it's not really super complicated. The intuition is actually quite simple. basically you need to look in the DLA, what kind of operators can we construct which are invariant under this twirling channel. And therefore, if we find an operator that is invariant, we will be projecting onto that subspace. And it turns out that the only choice really is this quadratic Casimir operator, which is so defined from the elements of the Lie algebra. And therefore, we get this lemma, which is basically the solution of the problem, which is that the second moment of an operator, which is in the Lie algebra, this is very important, is given by a sort of an inner product with this Casimir operator. And you see, crucially, at the denominator here, we have the dimension of the DLA. And so you may see that this is where actually the conjecture is coming from. So this explains the conjecture. To be more precise, let me state the theorems that we proved. So it's two separate, very similar theorems. One is on just the variance of the cost. And yeah, this is the simpler version, let's say. And this is like the true OG Barren Plateaus, which is the variance of the gradient. They're very similar. There is only one extra term. Also, I should say these are theorems for the simple groups. But you can generalize this very easily to general compact Lie groups, which covers all possible dynamical Lie groups. Okay, and to explain these theorems, let me introduce two important quantities. The first one's super important. You're going to hear all about this from Michael, so I'm not going to say too much about it, other than it's the G purity. We write it like this. Is a property of a general operator, which might be the state as well, and is basically the purity on the DLA subspace, and it's defined using the Casimir operator. And then I also define this Killing norm here, which is, you can understand it as a Frobenius norm in the adjoint representation. It's not that essential, but it's that element here, and it's basically the difference between the two. So you see these two are very related, and in fact, they are two sides of the same coin. Usually you only need one of the two to prove Barren Plateaus. Okay, cool. And finally, before passing on the mic to Michael, let me showcase that this actually works. So first of all, let me remind you that we actually were able to present an exact solution. So while the conjecture was just a bound, this is really an exact solution. And to prove it to you, this is an example. So these are called compound layers. I won't go too much into the details, but they're also called orthogonal layers. They're related to match gates, etc. They're very nice. You can do very nice things with them. And they had been conjectured to not have Barren Plateaus, but this was impossible to prove previously. And thanks to the theorems, we were able to prove it, and in fact show that not only it seems to be like very close to the actual behavior, but notice that here, this is like the theorem is in a general, like the integral over the entire group, and we have no guarantee really that this is converging always to the hard distribution very fast. It eventually will, but we don't know if it's fast or not. But we see here that indeed it seems to be almost an exact match. So this suggests that the convergence is indeed very fast, and that these results apply in practice. And so now, yeah, I'll pass it on to Michael to talk about the interpretation of these results.
Well, thank you for walking us through the mathematics side of this. And so I get to zoom out a little bit and talk a little more about interpretation. So just to kind of recall what Enrico has already told us about Barren Plateaus, I really like, so I'm a terrible hiker, and I like to imagine that Barren Plateaus when you're a variational algorithm going on a barren plateau, it's kind of like when I'm hiking, because I always look at my feet, and so I can only really make local steps. And if I'm in a barren plateau, I'm going to get lost. I have no idea where to go. I don't have enough local information. It's not wiggly enough for me to move. But if I don't have a barren plateau and I look around a little bit, even though I'm still looking at my feet, I'll at least get to the top of something. So that's kind of a mental picture I like to have. So let's think about this formula, because we've said that this is going to unify what we know about barren plateaus. So we've had something like 5 years of results for barren plateaus that are sort of piecemeal, where we have different insights into what can cause a barren plateau, but they're sort of not so connected. So let's take a look at this formula again. We'll look at the loss function version of it, and I want you to notice a couple of pieces. So we have this dynamical Lie algebra. Notice the dimensions in the denominator. So as that thing grows, we're going to see that this variance shrinks. We also have this G purity quantities. So as those shrink, the variance is going to vanish. So before we move on, let's think a little bit about this G purity. So pick your favorite subalgebra. It's certainly a vector subspace, and so we can talk about projecting onto this vector subspace. So the G purity of a Hermitian operator, project onto your subspace, then compute the purity of that thing. So just as sort of a mental check, if you compute the purity of something that's already in the dynamical Lie algebra, it's just the purity. The G purity is exactly the purity. So all it can really do is shrink the purity of some operator. All right? So let's think about the very first barren plateau result. So this is kind of a circuit expressivity statement. So the first insight was that when you have a 2 design, we're going to get a barren plateau, regardless of your choice of input state or observable. So how does this sort of fit into the Lie unification picture? Well, if you have a 2 design, this dimension of the dynamical Lie algebra is going to scale exponentially. It's huge, and so you're going to get a highly expressive circuit. This dimension's enormous, and your variance is going to be tiny. So just one way to think about it is it's kind of a no free lunch type theorem. If you can train whatever quantum circuit you want, that's a little too powerful. You can start handling problems that you shouldn't be able to handle. So what else can happen? So one of the well-known sort of things that can cause a barren plateau are these entanglement-induced barren plateau. So suppose you have a local observable, you have some highly entangled input state. This means that when you look at that local observable, this thing is going to look kind of like a maximally mixed state, and this is going to lead to a barren plateau. So what's causing it here in the Lie unification picture? So the G purity of this input state is going to get very, very tiny, because it's kind of like a maximally mixed state there. It's worth mentioning that in the paper, we actually calculate exactly the states which maximize this G purity quantity, and they are highest weight vector states, rho. So maybe you think, okay, well, certainly I shouldn't use a local observable. Maybe that's the problem. Oh, no, it's not. Global observables are actually the problem. So if you do global measurements, you're going to get barren plateaus. This was first realized back in 2021. So what's happening with the G purity picture? Well, if I have a global measurement 0 and I compute its G purity, I have to project onto my algebra, that's going to kill off a bunch of this purity term. So it's worth reminding yourselves that the more that this observable overlaps the dynamical Lie algebra, the more G purity you have to work with. But the algebra can't be too big because we don't want a highly expressive circuit. So it's kind of like you're projecting onto a tiny subspace. That's one way to sort of think about it. And then finally, I'm going to mention noise-induced barren plateaus. So here, the two sort of offending terms are these 2 G purities of either the input state or the observable. So the more that this noise sort of hits it, this could change your G purity. Now, this is a little bit subtle because really we care about noise that changes it outside or within the dynamical Lie algebra. So for instance, local unitary rotations they don't change purity, but they could change G purity. So these are things you sort of need to consider when you're trying to detect a barren plateau. So just some open questions before we sign off. So one of the realizations that we've had is that every trainable model that we have, meaning doesn't have a barren plateau, is also classically simulable. Now, this is kind of leaves this big open range of can we actually find interesting VQAs? That's kind of a big open question we'd like to think about. And closely related to this, and I'm going to put a plug in for Boshko Bakalov's talk tomorrow. And one of the big questions I'd like to know is whether there are interesting dynamical Lie algebras that scale in between quadratic and exponential scaling. Now, to kind of appreciate why this is interesting, go to Boshko's talk. So there's also this question of, we have this very key assumption of the Lie algebra supported ansatz. Relaxing that is quite difficult. Now, really, I don't think we should put too much effort into relaxing it until we have sort of some interesting observables to think about or interesting problems to think about. But that is a direction we're curious about. And then one of the things that Enrico pointed towards was that we have some evidence that these things mix quickly, but it'd be nice to have some more quantitative estimates on how quickly it converges to the Haar measure. Thank you for your time. And we, of course, welcome your questions.
Hey, thanks. That was a really nice talk and a really interesting result. I guess my first question is, so you've got some really great intuition now as to why these kinds of Barren plateaus form. Do you have any intuition for why our trainable models are classically simulable? Is it just that the space is small, or is there something else?
I guess the short answer is there is no definitive proof, but there is a paper that has been released relatively recently about this, sort of trying to formalize this connection. And I think the argument that's made there about classical simulatability, if I understand your question correctly, is that essentially there seems to be, whenever you can prove the absence of a Barren plateau, it seems that the proof in itself implies that the dynamics that you're interested in, the interest in dynamics, is constrained to a subspace, a polynomially large subspace. Hence the classical simulatability. So, but it's very, very hand-wavy, and intentionally so, because there is no result yet.
Okay, but intuitively, we want a system where the dynamics are not constrained to a small subspace, but at the same time, we don't.
Yes, yes. It seems more difficult to come by, at least. Yeah, I mean, I'd be very interested if any one of you has a very nice counterexample to that. Yeah, I mean, that's definitely an open avenue of research.
Yeah, thank you.
Thank you.
Yeah, I had a quick question. Yeah, thanks for the great talk. So the dynamical Lie algebra stuff and kind of the result you hint at the end for it being classically simulatable, these are kind of in a way like infinite depth results. So they're sort of, if you were to keep generating the circuits over and over again and like you explore the entire space. So it's like kind of says, if it's easy to simulate, that's because in this circuit class, even if I went to infinite depth, I could never even find something that was like a 2 design, something I could make in like a couple of circuit layers. So that's kind of a tight restriction. But my question is there anything in this kind of Lie algebraic formalism that tells you about like finite depth circuits? Is there some like restriction you can introduce that says like, oh, it naturally falls out that small light cones or this particular initialization won't have this because I've restricted myself to depth 100 circuits? Or is this really only applicable in this like case where you generate the full groups, which might require some amount of depth?
Can I?
Yeah.
Or,
do you want to?
Let's both answer.
Go ahead.
Okay, I'll be quick. So, right. So the intuition I have for, well, first of all, there are some results out there that say that when you don't have uniform initialization, like, and you have instead, for example, Gaussian initialization, then you don't have Barren plateaus. I think what you're suggesting is slightly similar to that, because in a sense, if you modify your initialization, you're also failing to converge, to mix to the hard measure, at least if done carefully. So I guess the answer is yes, you could avoid Barren plateaus even in an exponentially big DLA. However, in that paper, the authors make the argument that that is still classically simulatable in a sense, because the dynamics is constrained in this sort of artificially smaller subspace, which is no longer the whole DLA, but it's some sort of effective subspace that is given by your failure to explore the entire DLA. I know this is very hand-wavy. That's how I understand that case, but there might be some middle ground that perhaps leaves some room there. Yeah, I'm not too sure, but maybe Michael has.
I don't have more to add.
Okay. Yeah, does that satisfy you?
Hi, thanks for the talk. Is it easy to decompose the dynamical Lie algebra into a bunch of simple ones plus a center?
Algebraically, yes.
Conceptually, yes, but I mean, given a concrete Lie algebra, is it easy?
Still pretty easy. I think the hardest thing is actually extracting what the entire dynamical Lie algebra is. So actually, one of the big questions we'd kind of like to answer is, I give you some set of circuit generators. What is the associated dynamical Lie algebra? So sometimes these algorithms converge very quickly. Sometimes they don't. I don't think we actually understand in general how long it takes to compute these sorts of things. So in practice, I don't know, we were able to compute quite a few. So I'm not too terribly worried about that. But like once you have the concrete algebra in hand, it's quite straightforward to see what the decomposition is. That's a great question.
So is there like general procedure, even if we are given the basis of the Lie algebra, is there a general procedure efficiently can compute the decomposition?
I don't know about efficiently, but certainly we can compute it on a laptop within a day.
Thanks.
Yeah. Like we haven't done any careful analysis. It's more just like, hey, numerics guy, can you help me out? And then he gets back to us by the end of the day.
Hi, thanks for the talk. This dimension of dynamical Lie algebra looks like have a relationship between operator spreading or information scrambling. Do you have any relationship between those?
I mean, that sounds very much like a different sort of interpretation of this expressibility idea. So I think they're very intimately related, yes.
Thank you for the great talk. I have maybe a naive question. What is the story like on the classical machine learning side? So, for example, in the deep learning world, are this Barren plateau an issue, and how they usually overcome this? And can your formalism, can we incorporate the classical story into your formalism in some way or another?
Yes, the short answer is in classical ML, you do have vanishing gradients. You also have exploding gradients. There's a lot more complexity, I think, in the classical side. Much of the niceties of the quantum side come from the fact that you're very constrained in the kind of operations that you can do, and you can never have exploding gradients. But yeah, I would say perhaps the message sort of carries over slightly from the classical side, but I don't think there is such a strong connection, just because the setting is very, very different. Yeah.
Okay. Thank you.